volumes using cylindrical shells. All right, the methods we've used so far to compute the volumes of solids depended upon us being able to find the cross-sectional area of the solid. In this section, we're going to find a way to compute the volume when it's too difficult to find the cross-sectional area, or maybe the integral we come up with is too difficult to solve. So this new method is called the method of cylindrical shells. So first let's talk about a cylindrical shell. A cylindrical shell is a solid enclosed by two concentric right circular cylinders, and the volume is going to be equal to the volume of your outer shell minus the volume of your inner shell. So that's going to be equal to pi times the radius of your outer shell squared times h minus pi times the radius of your inner shell squared times h. Now let's do a little bit of algebra here. We can factor out a pi h. Here we have the difference of squares, so we can factor that. And now let's rewrite this a little bit by multiplying and dividing by 2. And when we rewrite it in this way, what we end up with is 2 pi times the average radius times the height times the thickness of the shell. So the volume of a shell is equal to 2 pi times the average radius times the height times the thickness. So now, let's suppose we have a curve y equals f of x, and we look at the area below the curve and between the lines x equals a and x equals b. We're going to take this region and revolve it around the y-axis. When we do that, we're going to end up with a shape that looks somewhat like this. All right, kind of like a bundt cake. So what we're going to do is we're going to choose a partition of AB, and each partition, if we draw a vertical line at each partition point, that'll cut up this shape into slices. And here's the kth slice. So think about this. On our kth slice, the average radius is x sub k plus x sub k minus 1 divided by 2. And we're going to call that point c sub k. And c sub k is definitely in the kth subinterval. That slice, when we revolve it around the y-axis, is going to create something very close to a cylindrical shell. So we're going to let the height of this approximate the volume of that by the volume of the cylindrical shell of height f of c sub k. So that tells us, oh, I forgot, in our thickness too. The thickness of the shell you need on the kth interval is your delta x sub k. So now we can get that our volume for that shell is equal to 2 pi times the average radius times the height times the thickness. So if we approximate the volume of all the shells going around that way and add them up, that'll be a great approximation for the total volume of the solid. So now look at the sum that we've done. It's just a Riemann sum for the function 2 pi x f of x on the interval AB. So now if we increase n such that the norm of the partitions head to 0, then we can go ahead and say that our volume is equal to the integral from a to b of 2 pi x f of x dx. Or if you think about it, it's 2 pi times the radius times the height of the cylinder at x. All right? So it's easy to remember this formula. You just remember the surface area of a cylinder, put it in here, and you're good to go. All right, so now suppose I want to revolve it around a line x equals L instead of the y-axis. The only thing that's really changed is now the radius has gotten either bigger or smaller depending on where L is, right? So here's how we're going to do it. We're going to say our volume is still equal to, we're still taking our slices from a to b, so the integral from a to b, 2 pi times our radius. Well, our radius now goes from the line x equals L to x. So that's x minus L, and then the height is still the same, f of x. So here's our formula for the volume. And notice I put absolute values around x minus L. Well, that depends where L is. If L is less than A, then it's going to be x minus L. If L is greater than B, then it's going to be L minus x. So that's why the absolute value signs are there. All right, so let's do an example. Let's use cylindrical shells to find the volume of the solid generated when the region enclosed between y equals the square root of x equals 1, x equals 4, and the x-axis is revolved around the y-axis. So the first thing you're going to do is sketch the region. All right, so here's the curve y equals the square root of x. Here's x equals 1, x equals 4, and the x-axis. So if you look at those, the region enclosed by those is this green area here. Now what I want to do is I want to take that region and revolve it around the y-axis, right? And I want to use cylindrical shells. So if I'm going to revolve this way to get a shell, I need to make my cut perpendicular to the x-axis. All right? So our volume is equal to the integral from a to b. So a to b is where we're taking our slices. We're starting at x equals 1, and we're taking our slices up to x equals 4. And then it's 2 pi times our radius, which is from the y-axis to x, so it's x, times the height. So the height here is y equals the square root of x. So now we've just set up our volume formula, and it's up to you to evaluate it. Pause the video here, see if you can come up with the final answer. So your final answer is 124 pi over 5. All right, so that shape that we did wasn't too difficult. So let's try doing it again, but this time let's use the washer method. All right, so what we were doing is we were trying to find the volume of the solid generated when the region enclosed between y equals the square root of x, x equals 1, x equals 4, and the x-axis is revolved around the y-axis. So here's a sketch of the curves. And this time, I want to use the washer method. So when I spin it around this way, I want to end up with a washer. To do that, I need to make my cuts perpendicular to the y-axis. All right? So now, look at when I take my cuts perpendicular to the y-axis, to use my washer method, I need to know what my top function, my bottom function is. And clearly, x equals 4 is always going to be my top function. But between the regions y is between 0 and 1, my bottom function is a function x equals 1. When y is between 1 and 2, my bottom function is this function, which is x equals y squared. So when I go to find the volume, I need to set up two separate integrals. All right? So my volume is equal to, on the interval y is between 0 and 1, my top function is 4, and my bottom function is 1. Now to find the volume between when y is between 1 and 2, here's my integral from 1 to 2, and then it's pi times my top function squared minus my bottom function squared. So now that we have them all set up, pause the video, and go ahead and make sure you can calculate these. And when you're ready, come back and see the answer. So the answer is equal to 124 pi over 5, which, thank goodness, is the same as the previous example. We wouldn't want to have two different answers for the volume. So now let's do another example. In this one, let's use cylindrical shells to find the volume of the solid generated when the region R in the first quadrant, enclosed between y equals x and y equals x squared, is revolved around the y-axis. All right, let's draw a picture. And here's what it's going to look like. Here's your curve y equals x. And here's your curve y equals x squared. And here's the first quadrant. So here's the region that we're going to take and we're going to revolve around the y-axis. Now here it's a little different because I have two curves and my region isn't going all the way down to the x-axis. Well, we can still do this. So what was the formula? It was our volume was equal to 2 pi times our radius. Well, if I take a slice here, my radius is still x, times my height. Well, here our height, instead of being from our upper curve here down to the x-axis, it's only going from my upper curve to my lower curve. So my height is my upper curve minus my lower curve. So we set up our integral. It's the integral from 0 to 1, because that's how we're taking our slices, 2 pi times our radius times our height. So go ahead and pause the video, figure out what this integral is equal to, and then come back. And when you're done, you should have gotten that this was equal to pi over 6. Alright, so let's do another example. This time we're going to use a cylindrical shell, but we're going to rotate about the x-axis. So let's use cylindrical shells to find the volume of the solid generated when the region R under y equals x squared over the interval 0 to 2 is revolved about the x-axis. So first let's draw a picture. Here's the curve y equals x squared over the interval 0 to 2, and we're going to revolve it around the x-axis. So this time I'm revolving around the x-axis. I want to use cylindrical shells. So to get a shell, when I turn it around this way, I got to make my slices here, perpendicular to the y-axis. Now what do I need to know? I need to know my radius. My radius is the distance from the slice, which is at y, to the x-axis. So my radius is y. And I need to know my height. And my height is my top curve, which is 2, minus my bottom curve. And since we're going to integrate with respect to y, you want to rewrite your equation so it's x equals some function of y. So we get x is equal to the square root of y. So here, this height here is 2 minus the square root of y. Now, we set up our integral. Our slices are going this way, perpendicular y-axis, so we're starting at y equals 0 and we're keep slicing up to y equals 4. So our integral goes from 0 to 4, and then we end up with 2 pi times our radius times our height dy. Okay, so pause the video, practice taking these integrals, and now we can see that our volume is equal to 32 pi over 5.